Hi everyone, welcome to Differential Calculus. Today we explore lesson 2.3, computing limit. Number one, the limit laws. We need to know the limit laws because it will offer us the shortcut and we don't have to use the table. There are multiple limit laws. The first law is limit x approach a of a constant is a constant. Limit x approach a of x equal a. So as you can see in the second law, it looks like we are doing a substitution. Sub x for a. In C, we can break up the limit. In D, same thing. We can break it up. And similarly for E, we can break it up. In F, the limit of a composition of function is going to be the function of the limit of the inner function. And then for limit x approach a of a constant c multiplied to the function, we can always pull the constant c outside because the limit is about a function. Let's take a look at an example here. Example. Compute limit x approach 1 to x squared minus x plus 1. This is limit x approach 1. We can use law C to break it up. 2x squared minus limit x approach 1 of x plus limit x approach 1 of 1. And then from here, we can use law G, move the 2 outside. Limit x approach 1 of x squared. Well, this is the direct substitution from law B1. And the last limit comes from law A1. Now we can use law F2. Limit x approach 1 of x squared minus 1 plus 1. So it's 2 from law B. We have 1 squared minus 1 plus 1 is gone. So the limit is 2. Notice that we can do this a little faster. 2x squared minus x plus 1 is a parabola. So we can just sub in x equal 1. Notice that limit x approach 1 to x squared minus x plus 1. We can just do a direct sub here. Then we have 2, 1 squared minus 1 plus 1, which is also 2. Pretty amazing, huh? So that led us to limit using direct substitution. I have an example here. Limit x approach to x squared minus 4 over x minus 2. If we attempt to do the direct sub right away, then sometimes it works, sometimes it doesn't. 2 squared minus 4 over 2 minus 2. We get 0 over 0. It doesn't mean anything. However, we can factor the expression. And if we factor the expression, then we have limit x approach 2, x minus 2, x plus 2, and down here is 1 times x minus 2. The x minus 2 cancel out. So what we have is just limit x approach 2 of x plus 2. And now we can use the direct sub to get 2 plus 2, which is 4. Beautiful. Here come a direct substitution rule. DS rule. If x equal a is in the domain of f, that means the function is defined at x equal a, then limit x approach a, fx can be computed using substitution f of a. If x equal a is not in the domain of f, then simplify f into g so that x equal a is in the domain of g. If that is possible, then if simplifying is possible, then limit x approach a, fx is the same as limit x approach a, gx, and that is g of a. Beautiful. Let's apply the direct sub rule to do a few more example. Example, compute limit. First example, we have limit x approach 2, x squared minus x minus 2 over 2x squared minus 5x plus 2. We can factor this rational expression. Limit x approach 2, x minus 2, x plus 1. On the bottom, we have a 2x minus 1, x minus 2. Yay, and then we see that, ta-da! The fact that x minus 2 cancel out. And so we have a limit x approach 2, x plus 1 over 2x minus 1. Now we can do the direct sub. Direct sub, and we have 2 plus 1 over 2 times 2 minus 1, which is 3 over 3. That's 1. Yay! Got 1. In B, well, if you say square root, usually you can multiply by the conjugate. Let's multiply by the conjugate. Multiply by root x squared plus 9 plus 3 over root x squared plus 9 plus 3. And this, in case you want to do a little review, is called the conjugate. Limit x go to 0. X squared plus 9 minus 3 squared over x root x squared plus 9 plus 3. So x squared plus 9 minus 9 will give us just x squared over x root x squared plus 9 plus 3. The x when x gonna simplify. So limit x go to 0. We have x over root x squared plus 9 plus 3. And so from here we can do a direct sub, which gives us 0 over root of 0 squared plus 9 plus 3. So the bottom is non-zero and the top is 0, which means that the quotient is 0, and that is the limit. Amazing. One more. In C, in order to compute the limit, we got to do the common denominator. Don't multiply everything by the denominator. We want to figure out the least common denominator, the smallest one. So it is best that we can do some factor. 1 over x minus 1, and then this 1 over x minus 1, x minus 2. Yay, which means that LCD is x minus 1, x minus 2. And so we can get a common denominator here by multiply the first rational expression by x minus 2 over x minus 2. Limit x approach 1. X minus 2 plus 1 over the common denominator. X minus 1, x minus 2. Limit x approach 1. X minus 1 over x minus 1, x minus 2. We can factor out a 1 from x minus 1. And then from there, we can cancel the common factor. So limit x approach 1 of 1 over x minus 2. And now the direct sub going to give us 1 over 1 minus 2, which is -1. Beautiful. Let's move on to 3. Squeeze theorem and limit involving sine cosine. The Squeeze theorem states that if gx is less than or equal to fx and less than or equal to hx, that means the function fx is between gx and hx, and the limit of gx is the same as the limit of hx as x approach a equal L. Then the limit of the middle function fx as x approach a has to also be L. Let's apply the Squeeze theorem to this example. In the first example, we want to figure out the limit x approach 0 of x squared times sine of 1 over x. Well, 1 over 0 is undefined. We don't want that. So that is why it is best to notice that sine 1 over x is between -1 and 1. Therefore, we can multiply by x squared. So -1x squared less than or equal to x squared. Sine 1 over x less than or equal to 1 times x squared. And we have minus x squared less than or equal to x squared sine 1 over x less than or equal to x squared. Now we can take the limit. Limit x go to 0. Limit x go to 0. Limit x go to 0. Notice that limit x go to 0 of negative x squared. Let's do a direct sub here. 0. And similarly, limit x go to 0 of x squared. From the direct sub, we get 0. And therefore, you see that limit x go to 0 of x squared sine 1 over x is between 0 and 0. So by the Squeeze theorem, limit x go to 0 of x squared sine 1 over x has to be 0. Wow, beautiful. Similarly, if you look at this problem here, root x e to the cosine pi over x, right? We have pi divided by 0 on the right side. For cosine, it's not simple because cosine go up and down. Yay. So best way to approach this limit is by take a look at cosine. So when the cosine pi over x is between -1 and 1. Same trick. Next, we take e to the -1 less than equal to e to the cosine of pi over x less than equal to e to the 1. And we multiply by root x e to the -1 less than equal to root x e cosine pi over x less than equal to root x e to the 1. And now we can take the limit. Limit x approach 0 on the right side of root x e to the -1 less than equal to limit x approach 0 on the right side root x e to the cosine pi over x less than equal to limit x approach 0 on the right side root x e. Yay! And from the direct sub, well, we get a root of 0 times a number that's non-zero. It's going to be 0. Limit x go to 0 on the right side, root x e to the cosine pi over x, and similarly on the right side it's also 0. So by Squeeze Theorem, limit x go to 0 on the right side, root x e to the cosine pi over x is 0. Amazing. One more thing is to figure out limit of absolute value and piecewise function. Here's a refresh on limit of the absolute value. So absolute value x equal to x if x greater than or equal to 0. Negative x if x less than 0. We can replace x by a. So it's a if a is greater than or equal to 0 minus a if a is less than 0. And use this definition to rewrite the absolute value function as the piecewise function. From here, we know that x squared plus x minus 6 over x minus 2 absolute value is, we can divide this into two pieces. X squared plus x minus 6 over x minus 2 if x minus 2 greater than or equal to 0. X squared plus x minus 6 over minus x minus 2. That is the negative a. If x minus 2 less than 0. Let's simplify this one. We can factor the top to be x minus 2, x plus 3 over x minus 2. If x greater than or equal to 2 on the bottom, that is the second piece. Same thing, x minus 2, x plus 3 over minus x minus 2 if x less than 2. And so we have two pieces. One is x plus 3 if x greater than or equal to, the other one is minus x minus 3 if x less than 2. Now to find the limit as x approach 2, we need to figure out the limit as x approach 2 on the right side, on the left side, because we define the absolute value function as the piecewise function, and it has two pieces. Limit x approach 2 on the left side of fx is, well, use the left piece, limit x approach 2 of minus x minus 3. It's also on the left side. From here, we can do a direct substitution. So it's minus 2 minus 3, which is minus 5. Limit x approach 2 on the right side of fx is limit x approach 2 on the right side of the right piece, x plus 3. Do the direct sub, we get 2 plus 3, and that is 5. Oh, the two limits are not the same. So limit x approach 2 of the absolute value function is d and e does not exist. The cool thing about figuring out the limit is that it allows us to sketch the absolute value function. We can actually sketch it. X, y. So as x approach 2 on the left side, the output is negative 5. Negative 5. And because x does not equal to 2 on the left side, we use an open circle. Yay. Go up. Reason why, because negative x minus 3 is a straight line. Now, limit as x approach 2 on the right side is 5, and x does equal to 2. So we use the solid circle. Straight line. Yay, this is the graph. Awesome. Let's do another example. Last one. Limit x approach 1 of fx, where fx is the piecewise function. X squared plus 1 if x less than 1, and x minus 2 square if x greater than or equal to 1. We have limit x approach 1 on the left side of fx, and that is the same as limit x approach 1 on the left side of x squared plus 1. Do a direct sub here. 1 squared plus 1 equal 2. Limit x approach 1 on the right side of fx. We use the other piece, limit x approach 1 on the right side of x minus 2 square. Do a direct sub, and we have 1 minus 2 square, which is 1. Well, the limits are not the same. So limit x approach 1 of fx is d and e does not exist. We can use the limit of the piecewise function to sketch the piecewise function. Let's do it. X, y. Well, we have 1 right here. On the left, piece x squared plus 1, meaning that we're going to shift the function up by 1 unit. And as you can see, the limit as x approach 1 on the left side is 2. Well, since we don't have equality, we use an open circle. This is a parabola. Okay, got the left piece. Next is focused on the right piece. The limit as x approach 1 on the right side is 1. So it's going to be a solid circle. And x minus 2 square tells us that we shift the parent parabola x square to the right 2 units. So this way it look like. Wow, pretty cool. And a good review on translation of function. Thank you for watching. I hope you found the content useful. See you in the next video.